A very good morning to everyone. I am G. Naresh from ECE section, IARE College. My Tech Talk topic is about physical layer security performance of wireless mobile sensor networks in smart city. This is a PPT of wireless sensor networks subject. Let's get into the topic. Introduction. The physical layer security performance of wireless mobile sensor networks WMSN in a smart city is a critical aspect of ensuring data privacy and security in urban environments. In these networks, sensor collects data for various smart city applications like traffic management and environmental monitoring. Physical layer security focuses on safeguarding this data by preventing unauthorized access or airdropping. This it uses techniques like signal encryption and interference manipulation to protect the wireless communication between sensors and central system. Ensuring strong physical layer security is essential for maintaining the confidentiality and integrity of sensitive smart city information, making our urban spaces safer and more efficient. System model. Figure 1 shows the multiple antenna wireless sensor network model in smart city. This is the figure 1 which shows the multiple antenna wireless sensor communication network model based on wireless wiretap model. The system includes a mobile source sensor which is S and a mobile legal destination which is denoted as D, and the mobile AOS dropper which is E. Sensors. S sends information to D. The source sends the information to the destination. E can obtain the information via AOS dropping channel. The S is equipped with NT antennas. The D and E are equipped with single antenna. In the following, H denotes the channel coefficient which follows two Nakagami distributions, which is H equals to L equals to 1 to 2 AL, where AL is a Nakagami distribution random variable. The probability density function is given as f of a is equals to 2m power m by pi power m gamma of m and a power 2m minus 1 expression of minus m by pi m by sigma a square, where m is a fading coefficient and 2 ohm is equals to e into a of is a scalar factor. E of dot denotes the mean value and gamma denotes the gamma function. Here, as we mentioned previously, the S is a source and D is the destination and E is a channel. The probability density function of H is given by f of H is equals to 2 by H into pi of t is equals to 1 to n gamma of mt g of 0 comma 2 to 2 comma 0 into h square of pi of t equals to 1 to 2 mt by ohm t, where m1 is m1 and m2, where g of is the Myers G function and VSD is the relative gain of the S and D link, and VSC is the relative gain of the S to E link. D and E receives the signal as gamma SDI is equal to under root of VSD E HSDI into X plus NSDI, and gamma of SEI is equals to under root of VSE into EHSEI into X plus NSEI, where X is the transmitter signal which has mean 0 and variance 1. SDIN and SEIN are additive white Gaussian noise, that is AWGN, which has the mean 0 and variance 0 n0 by 2, and E is the emission power of X. The corresponding received signal to noise ratio at D is given as gamma SDI is equals to KVSD and HSDI square into E by N naught. The average received signal to noise ratio is given as gamma SD bar is equals to KVSD into gamma bar, where gamma bar is equals to E by N naught, where K is the signal to noise ratio gain of the main channel relative to the eavesdropping channel. The corresponding received signal to noise ratio at E is given as gamma of SEI is equals to VSC into HSEI square into gamma bar, and the average received signal to noise ratio at E is gamma SC bar is equals to VSC into gamma bar. The probability density function of gamma K is given as F gamma K of R is equals to 1 by R into pi of I is equals to 1 to N gamma of Mi into G of 0 to 220 into R by gamma K pi of I equals to 1 to 2 Mi by ohm I, where M1 M2. The instantaneous security capacity is defined as Ci is equals to maximum of ln, that is natural logarithm of 1 plus gamma of SDI minus natural logarithm of 1 plus gamma of SEI, comma 0. For the optimal TAS scheme, we select the transmit antenna W as W is equals to maximum of Ci, where 1 is less than I is less than NT. For the suboptimal TAS scheme, we select the transmit antenna G as G is equals to max of gamma SDI, where 1 is less than equals to I is less than equals to NT. Simulation results. In this section, the channel are adopted has two Nakagami channels E is equals to 1 and gamma is equals to 10 dB. The table 1 shows the stimulation parameters, where the parameters and the equivalent values are given, where MSD is equals to and MSC is equals to 1 and VSD and VSC is 5 dB and NSD and NSC are 2 and NT is 1, 2, 3 respectively, and gamma is 0 dB. These are the figure 2 and figure 3. Here the figure 2 shows the SOP performance of the optimal TAS scheme, and the figure 3 shows the SOP performance of the suboptimal TAS scheme when NT is equals to 1, 2, 3 respectively. The graphs are drawn by K in dB in the x-axis and SOP in the y-axis. Here the lines are the simulation results and the small squares are the theoretical values. In the figure 2 and 3, the SOP performance of the two TAS schemes are presented. The table 1 shows the Monte Carlo simulation parameters as shown in the figure 2 and 3. The analytical results match the simulation results well. For fixed NT, as the value of K is increased, the SOP performance improved. For fixed K, as the value of K is increased, then the SOP performance also increases. For fixed K, increasing the number of NT improves the SOP performance. Increasing K improves the SOP performance of the two TAS schemes. The SOP performance gap is also increased. When K is equal to 10 dB, the SOP is 9.2 into 10 to the power of minus 2 for the optimal TAS and 1.4 into 10 to the power of minus 1 for the suboptimal TAS scheme. Physical layer security, which is shortly known as PLS, is the context of wireless mobile sensor networks WMSN in a smart city, essentially mean using the unique characteristics of wireless signals to keep the data transmitted by sensors safe from eavesdropping or hacking. Think of it like this: in a smart city, there are lots of sensors scattered around, collecting and sending data wirelessly. This data can be sensitive, like information about traffic, air quality, and surveillance. To protect this data, we can use the physical properties of wireless signals, like how they travel through the air, to make it hard for unauthorized people to intercept or understand the data. So, physical layer security is WMSNs in a smart city is all about using the clever tricks of wireless signals to keep the data safe for prying eyes, making sure that only the intended recipients can access and understand it. In conclusion, the physical layer security is a vital aspect of ensuring data security in wireless mobile sensor networks deployed in smart cities. By leveraging the inherent properties of wireless signals, PLS helps protect sensitive data from unauthorized access and interception. This security measure ensures that only authorized parties can access and decipher the transmitted information, contributing to the overall safety and reliability of the smart city applications. Thank you.